Good evening, dear all. Let us today understand the topic of electric field. Whenever we start a new topic, we must connect it to the old topic. Our old topic was Coulomb's law of forces, which stated the force between two charges Q1 and Q2 kept at a distance r. So, relating that topic to the new topic, electric field, we are asking a question to ourselves: why was this force of repulsion or attraction between these two charges? What was the reason for the force? The reason for the force is the charge placed in a medium has its own electric field around itself. At present, let us keep the topic of electric field aside and let us imagine or understand what can be happening if I place a magnet in some medium. Let it have one north pole, let it have one south pole, and let me place one small safety pin in front of it. We will be immediately able to see that this pin gets attracted towards this particular magnet. If I place it very far, it may or may not be attracted. So, to understand why this has happened, we said that there is a magnetic field which exerts a force on this pin and makes it attract towards the magnet. Correct? So, around the magnetic field, around the magnet, there is a magnetic field due to which this pin moves. Similarly, around a charge, there may be some field which will help it to move the charge towards it or away from it. This pin we used as one tester to understand whether the field is there here, magnetic field is there here, whether magnetic field is there here, where is the magnetic field finishing. So we use one safety pin as a test magnetic material to understand where is the magnetic field. Is it there here or is it not there here? Similarly, let us now move towards the charge placed at the origin O. I have rubbed the figure of the magnet and the safety pin which I had drawn only to understand the similarity between the magnet having a magnetic field around it and a charge having electric field around it. To understand whether magnetic field is there, we used one test pin. Similarly, to understand whether electric field is there around the given charge Q, we must use a test charge. Correct? So let us consider a charge Q whose electric field we want to know, placed at the origin O. Let us consider another small charge plus Q is equal to 1 coulomb as a test charge. We want to know the electric field of this charge. So let us call this as the source charge. Okay. So we want to calculate the electric field produced by the source charge. So we have placed one test charge at a distance r from it. This test charge should be positive, should be small. So we have taken its value as 1 coulomb. So from the Coulomb's law of forces between two charges, definitely these two charges will repel each other. So if they will repel each other, they will repel along the line joining these two charges. Okay, so this is the direction of force exerted by this charge on this charge. What is its value? F is equal to K Q upon R square, where we have already written Q is equal to 1 coulomb. Correct? So let us substitute the value. F is equal to K, Q we don't know, into 1 divided by R square. So what is this? K Q by R square. This force is given as the electric field due to the charge Q at a point P placed at a marked at a distance R from Q. Now let us define the electric field. The electric field due to the charge Q at a point P in space is defined as a force that a unit positive charge of 1 coulomb would experience if placed at that point. That's why when I took the value of the test charge as 1 coulomb, I consider that what force I have got is the electric field itself. Okay? Clear? Okay. So, now what if I take the charge more than 1 coulomb? Then how do I find out the electric field? So, we have another definition for electric field which we will find just now. Okay. So, let us take the charge Q which is not equal to 1 coulomb. Correct? Okay. So, now what can we do? Let us again calculate or write the magnitude of force between these two charges. F is equal to K Q upon R square. I am just talking about the magnitude. But this portion is just now written as E. So let me write F is equal to EQ. Am I right? So what can I write? Electric field is equal to the force between the two charges per the unit charge. So another definition for electric field is the force per unit charge, and its SI unit is given as Newton per coulomb. This is the SI unit of electric field. Okay. So if we want to now mark it vectorially, we have to understand the direction of the electric field due to the source charge. Fine. So we have defined electric field and we have written two formulas of electric field. Now we will understand how to denote the direction of electric field mathematically and draw the direction of electric field around the charge Q, that is the source charge. So let us first write down the formula as written here. Now how do I denote the direction of electric field? As you can see, E is inversely proportional to R square. So it means that E is a function of R, that means depends on R, and here I write R unit vector, which means that E is a function, electric field is a function of R, and R is a unit vector representing the direction of electric field. Similarly, here also I write E as a function of R and F is also as a function of R. It means the direction of electric field is the direction of the force itself acting on the test charge. Clear? So now taking the knowledge that the electric field direction and the force direction which is acting on the test charge due to the repulsion of the source charge, we can draw the direction of electric field around a positive charge Q and around a negative charge Q. Correct? So first remember that a test charge should always be positive and its value also should be small. So now we draw the direction of electric field around the positive source charge, placing positive test charge plus Q around it. Okay, and as we know from the definition, electric field of this charge is the force on this charge. Okay, so and there is a force of repulsion. So what shall we do? We shall directly draw a line joining these two charges. Okay, fine. We can take as well more number of charges. We can do that, right? Okay, placing positive test charges as many as we want around the positive source charge. Now, for a positive source charge, it means that the direction of the electric field is radially outwards, So remember this. The direction of electric field around a positive source charge is radially outwards. Fine? Okay. Similarly, let us draw the direction of electric field around a negative source charge. Same way we can draw keeping a test charge. Remember, test charge is always positive. So if test charge is positive and source charge is negative, there will be an attraction between them. So the force which will be exerted on the test charge is towards the source charge which is negative. So let us draw the direction of the force due to the source charge on the test charge. Okay, these all are attractive forces. Fine. So as you can see, they are all directed radially inwards, provided the source charge is negative. So remember that if the source charge is negative, then the direction of the electric field is drawn radially inwards towards the negative source charge. Clear? Okay. So you can understand the difference and draw it. As you can see. As you draw, you will be able to understand it better. So please make a rough note of whatever is shown or taught to you. So let us write features of electric field, keeping in mind that the test charge is a very small quantity. Now, sometimes the formula of electric field is also written as electric field vector is equal to limit q tends to 0 vector F upon Q. Now here you can see limit Q tends to 0 means the value of the test charge is very small but not 0. The question PYQ asked is what is the significance of limit Q tends to 0? The significance is if we take a source charge which is a large amount, and if we take a test charge which is of a very small amount, say 1 coulomb, then the electric field due to the test charge must not affect the electric field due to the source charge and move the source charge. It means because we have taken the test charge very small, it will not affect the electric field of the source charge, and we can calculate the electric field of the source charge because electric field is inversely proportional to R square. If at all we take a bigger test charge, then the electric field of the source charge will be affected. Correct? So, in order to maintain the electric field of the source charge at a particular distance R, we take this as a small test charge. Fine? That is the significance of limit Q tends to 0. Now, the second feature is, as you can see here, I have drawn, and here also I have drawn the radially outwards direction of the electric field for a positive source charge and radially inward direction of the electric field for a negative source charge. This is a board and it is a plane. So, does the electric field is the electric field drawn only on a plane? No. It is drawn on the three-dimensional value of the radius. That means consider the source charge to be placed at the center of a sphere such that the electric field is drawn or is available radially outwards on the surface of the sphere if the source charge is positive. Similarly, radially inwards for a source charge negative. So, what is it? That the electric field is three-dimensional for the value of R. Okay, that is the distance between the source charge and the sphere. Fine. Now let us come to the third feature, where as you can see from the definition, E is equal to, I am just writing the scalar quantity, that is the magnitude of electric field. You can see E is inversely proportional to R square. Right? What does that mean? That around the same R or for the same R around the source charge, the value of E is the same. Similarly, here also if I consider this as R, this as R, this as R, this as R, magnitude of electric field will remain the same because E is inversely proportional to R square. So what does this tell you? That the magnitude of the electric field is having Spherical symmetry. What is the meaning? That if I consider the charge to be at the center of a sphere, then the value of the electric field will remain the same provided the sphere has the same radius inwards or around the source charge. That means the electric field magnitude has spherical symmetry. Fine. Direction will be different as shown here, but magnitude will have some spherical symmetry. It means that around the source charge in a particular sphere, the magnitude of electric field will remain the same as the radius is the same in the sphere around the charge, source charge, whether positive or negative. Fine. So these are the features and the way we draw the direction of the electric field. Now I will just move away from the board. You write it down as a note because all this you have to apply in the numericals. These are all small points, but they are all PYQs and they are all going to be applied in the numerical. Okay.